Oops. Let's go back over here. So we didn't complete ourselves out and talk about several parts here. We'll do this and one other problem, and we're going to call it good. So let's go back and look at our drawing. Okay, let's review a little bit. I had my initial picture. I went through the discussion of Reynolds transport. I talked about continuity, and then I started thinking about momentum, and I realized, okay, Reynolds transport doesn't really add anything to your knowledge base when it comes to continuity, but the way you put it together is such that it does. And then when you add the extra velocity term right here, you end up changing from continuity to momentum. Okay, so we talked about this, we did this. We took I generally like to do this, take the left-hand side is basically the sum of the forces, and the right-hand side is another picture which has all the velocities on it, and it basically is associated with this. That's just my style of doing things. Now, if we come in and look at this, and this is the next important thing, is what type of forces exist on a fluid. You generally have two types, what are called body forces and surface forces. Now, here's a surface force, okay? Basically what a surface force is we have defined this as being our control volume. And I made that, this is not part of the control volume, I just did that to add so I can have an erasure point. Basically, you do like that and it erases. So the key is, what is the surface to that? Every part that's green. What is the volume? Everything that's in there. Okay, so let's really look at what that means. Well, and the way I'll do it is I'm going to copy this thing and I'm going to erase it as I'm talking about it, but I'm going to basically drop it right here and I'm going to talk about it. Okay, so it's pretty obvious that you got all these surfaces here. At this, this, and this one, and this one. Well, those are just listed straight up. There they are, right there. Here they are, not kind of in order, but right there. And here's 3 right here. Here's 4 sitting right there. These are all surface forces. So all you're doing is taking care of this. What is this? Believe it or not, this is a surface force as well. Now it may not make sense, but let's think about this for a minute. I put this in as Fx. Now, let's do this. Okay, as I go through and erase everything that I wrote, I identified all of those spots as green surfaces. Now, I'm going to identify the surface with this blue. This is the ones that are not the exits and entrances. You know what? I probably, since I already have that, I'm going to use. This is the surface of the metal jacket or wooden or aluminum or whatever this is that is forcing the fluid to go in the direction it's going. Now, I'm going to go in and zoom in a portion of it. And here's the flow coming in little vectors, and suddenly it reaches this wall, and bam, it's got to turn. So when it's turning, why is it turning? Because the wall is pushing back on it to force the fluid to turn this corner. Meantime, there might even be a little recirculation zone here, kind of creating a low pressure here, and definitely creating a high pressure here. Well, the compensation for that is that the metal jacket is not, and I keep calling it metal jacket, metal pipe or whatever, is not going to break, hopefully, So as it's turning the corner, and it's turning the corner here, so every time the fluid turns, there's some type of pressure forcing it to turn. Usually it's felt on the wall, and it actually is felt on this wall because it becomes low pressure here. So what happens here? Well, look at from this standpoint, okay? I'm sorry for copying this over and over, but hey, I'm trying to get the least amount of stuff in here as I can. So now you've got this metal jacket here, and it's devoid now of the fluid, let's say. So we're just going to try to reduce this down to this. So this is the metal jacket. So you got to think about it. What's in here is the water, and then you got the metal jacket. Well, if for a moment you imagine that you've removed the water, then you might have a pressure profile that kind of looks like this. In other words, might be higher pressure. It might get really high here because the water is pushing on this pretty hard. It becomes kind of a vacuum over here. So a low pressure here, and essentially a high pressure here might start off here, kind of get high, kind of get low. Eventually they're going to come out the exit. Now we haven't talked about this yet, but these are all exits. This is an exit. This is an exit. So in fact, the pressure at the exit is going to be, I'm going to list it as pressure gauge, which means it's going to be 0. Which means if I zoom in here and look at actually what the pressure profile might look like, it's going to go to 0 here. It might climb up really high here, and still might have a component here. So here, this one might, it's definitely going to go 0. It might, now if we want it to show it as a positive, here's what we might end up doing. Might end up doing it like this. So in other words, it's a vacuum, it's sort of sucking the wall to the right, but it is giving a force to the right. So if you go around and you add up all these, or you integrate, let's say you integrate, and I'm not suggesting we do this, but we integrate all the pressures in the D areas around the whole surface. The ones that aren't exiting, the ones that are here on the inside of the pipe, will all sum up to a particular force, Fx and probably Fy. And those forces are the ones that are listed right here. So in fact, these are surface forces. Now, what is a volume force? Well, that's the fact that maybe there's a certain amount of volume here and the water's pretty heavy. So, for example, and I didn't include it here, but for example, let's say you had a fairly large volume that was occupied by that pipe, and the water or the fluid in there was very heavy. Then essentially you would have this. Sorry, I'm eating a bar real quick. So in this one, okay, I mean here, as I'm going to take a pause to finish this. But I'm also going to go back and add a force here. Okay, sorry for my delay. I'm back with you. Let's say we had this. Let's say we had a particular force due to the body. What is that? That's nothing more than the gamma of the fluid and the volume inside of this. That's it. That's all it is. All that's the volume. That's all there is to it. So I'm going to go ahead and include that, but it doesn't appear here. There's no X component here. So again, these are all surface forces. There's nothing magical about it. So now, let's go in here and delete all that. Now, I never said anything about this, but now let's make the assumption that these are all exits. In other words, P2, P3, and P4 are all at an exit. And then let's just say P1 has to be a little higher to drive the fluid down here. So I don't know, 20 pounds. How about 2 pounds per square foot? So that's about 144, so that's 288 psi. So this would be 288 pounds per square inch, usually just written as psi. So 288 divided by 144 gives you about 2 pounds square foot. So what do you get? You get 2 pounds a square foot, and then 2 feet. You get nothing. You get nothing. Well, plus or minus nothing is nothing. Plus nothing plus fx equals 2. Okay, now I never figured this out, but I think I'll do that real quick. Okay, I think I have enough space up here to do this. Okay, so wrong button. Okay, now I got to go back to that. Now I got to go back to this. There. So 20. I'm just basically going to go from left to right and type these in kind of long form. 20 times 1.94 times minus 20 times 2 plus 20 minus 20 square root of 2 times 1.94. I wish I had a numeric pad. Times 20 times 0.5 plus 100 times 1.94 times 100 times 0.2 plus 33.3 divided by square root of 2 times 1.94 times 33 and a third times 0.3. Oh, I hit enter, nothing happened. Uh-oh. What's going on here? You gotta be kidding. Can it not calculate that? Never had that one. Oh. I have a mistake there. Okay. Okay, times 1.9 all the way to the end. Okay. Well, make sure that that seems correct. Well, 2510. I guess 2511. Okay. So 4 plus fx, we'll just say that. So fx is equal to 2507 roughly. Notice one thing. This isn't always the case. I made up this problem. There's not much that can be said about this in general. This is not a generic thing, but you notice the ratio of these two. Now, you can have situations where this one predominates, the pressures predominate the momentum. That is very common as well. Let's do the y component. Now, before I didn't have this. Now I added a particular volume. So now I have a body force that comes into the y equation. I did not include it before, so I need to include it now. So that's what I'm about to do. I'm about to include it. And so what I'll do is minus gamma times the volume in there. Now, again, these are all surface forces. This is a body force. The previous only had surface forces because the body force wasn't acting in the x direction. Now, we already talked about this pressure, and this pressure is 0, so what I get is Fy. Let's assume 62.4. Let's assume it's 3 cubic feet. And now, what I'm going to do, oh shoot, how am I going to do this? Okay. Here's the way I'm going to do it. Okay, so I'm going to grab this picture. Okay. Try to do the best I can about grabbing all of this. Coming all the way to here. Doing a copy. I'm going to go down. I believe it would fit right there. I am incorrect about that assumption, so I'm going to move it down to here. Then I'm going to eliminate this, and I'm going to copy this below it, and I'm going to say this is the y equation. Okay, let's take a look at this. Okay, again, on the left-hand side, you see my sum of the forces. My free body diagram is drawn right here. This is what I do in standard. On the right-hand side of this equal sign is only the velocities. So I can look up at the velocities and fill out the necessary pieces of information here. The equation itself is this is equal to that. Again, on the left-hand side, put the free body diagram. On the right-hand side, I put a picture. So that's why I repeated. This is just the way I do things. So I carried this out. Now I need to work on the right-hand side. So I'm going to change to this pen and say, okay, the y component of V1 does not exist. 0. The y component Vy2, whoa, it does exist. And it is 20 over square root of 2. Why is it 20 over square root of 2? I don't know if you remember this, but everything came out at 45 degrees. I don't know why this thing pops these things up. I wish I could figure out how to stop that. In other words, I made it 45 degrees, made that 45 degrees. This reminder is why I have 1 over square root of 2. So, now, I'll go ahead and copy this down, 1.94 for the density. V2 into, it is going out. Therefore, the dot product is positive, and therefore, this term is just plus 20. A2, I forgot. Looks like it's 0.5. I'm having trouble. Wish this thing would act a little better, a little smoother would be nice. 0.5. The y component of V3. There is no y component of V3. Therefore, that gives you 0. The y component of V4. Well, it's 45 degrees. So, the y component was 33 1/3, oops, and 1/3 over square root of 2, but it is going downward. Negative, upward, positive. Upward positive means that. So that's why you got a positive right back here. That's why you get a negative right here. Now, 1.94 is just 1.94. V4 N4. They're both going the same direction, positive. So the dot product is positive. So it's plus 33 1/3. Let's multiply. And I don't remember A4, which it was 0.3 feet squared. Okay. That's it. A lot less to calculate. I'll say Fy equal to, move this over, 3 times 62.4, 187.2 plus, now I've got to figure out this number and then this number, and I'm going to figure these out separately. Okay, 20 divided by square root of 2 times 1.94 times 20 times 0.5, 274.36 minus 33.33333. I'm just going to square that because there's two of them. Divided by square root of 2 times 1.94 times 0.3 gives you 457.26. So in this particular case, these were approximately the same order of magnitude. So, in essence, what you get is here, 187.2 plus 274.36 minus 457.26, and it's 4.3 pounds total. Now let's take it for instance. Let's just say, just for instance, that instead of this coming out at a 45-degree angle, it's shot straight down. Okay, if it's shot straight down, the square root doesn't exist. And so what you would have got is a larger number here. So, and that's for the exit at the bottom. Yeah, the exit at the bottom. So, that's pretty much that. Let's go and see if I can work this one real quick problem. Okay, I copied it. Did I put it in there? I don't remember. Did I copy it? Did I put it in there? Oh, geez. Did I put it there? Did I put it there? Well, here. Let's just put it here. I don't remember if I copied it. I could have swore I copied the thing. Up. Hello? Okay. Ah, there we go. Okay, here we go. A 10 millimeter, diameter jet deflected by the homogeneous rectangular block, which is that. It weighs 6 newtons. Determine the minimum flow rate needed to tip the block. Okay. Some assumptions. What do you say it was? 6 newtons. 6 newton. Now, if it's going to tip the block, he didn't say anything about the friction here. So I'm assuming the friction is large enough to offset this, and that the tipping of the block will occur. This has to be 6 newtons as well. So sum of the forces in the y equals 0 means this normal force, this normal force is back here. So now, the reason I placed it here is because the water is coming in and hitting this. We're going to make the grandiose assumption that the center of the force here is right there. And therefore, sum of the moments got to be equal to 0 right before it tipped the block. If there's no flow, here's what will happen. If there is no flow, this is going to sit straight under there. The more flow you get, this is going to adjust so that the moments are 0 until the point where it can't adjust anymore, and any greater force right here will tip the block over, because this can't move to here. You can only move to the edge. So sum of the moments tells me that this distance is about 0.05 meters. So if I sum the moment about here, oh geez, what's the width of this thing? Oh, it's right there. Sorry. Equals to 6, and we'll make that positive. 6 times 0.015 divided by 2, because this thing's halfway that far over. And then this is the force due to the water, and that's going to be minus the force due to the water and it has a little larger to go. Do I got that right? This, half of that. And so the force of the water got to be equal to, wrong thing. Let's move this down so that I can find, okay. 6 times 0.015 divided by 2, and then divide that by 0.05, 0.9, about 0.9. Is that right? times 0.05. Okay. 6 times 0.015 divided by 2. Yeah, that's right. So now that I've got that, here's what I can do. Okay. I'll go back to the book. What time is it? I need to make sure I'm not pushing the envelope here. There's my picture. Okay, I'm going to do my best. Where did it go? There it is. Okay. Over here. There it is. So, what do I have? I have the force of 0.9. And that should be in newtons, but that's okay. So now, what's the thing? Sum of the forces equals to the sum over the control surfaces of V. Now, what I'm going to do is I'm going to hack this up. Rho V dot normal times the area. Now, I'm only interested in the x component, so I can do this. Now, let's take a look at let's look at the surface. Okay, here's the controlled surface. Now, I can go back to here, and then go back to here, and I can define it that way. So I can have some water shooting out the top, water shooting out the bottom. This is great. I get water shooting in from right here. This is great. Now, he has no metal jacket around the outside edge. So I'm going to assume the pressure out here is 0, pressure out here is 0, pressure here is 0. Now, how is this actually really happening? It's happening by this. Okay. And I'm going to hack this up and then I'm going to delete it. So you've got a pressure profile here. In reality, what's happening is the wall is pushing back on the fluid because the fluid's pushing on the wall. Looks like that. So what is this? A surface force. And what is it equivalent to? Equivalent to that. These two are the same thing. Hang on. So this is the same thing as this surface force. So in fact, we can go in and look at this. Okay, so if I look at the left side, oops. If I look at the left side, I only see this. Now, let's look at the exit here. Okay. And since I have this here, I think I'm going to go get myself another copy of it. You know what? I may have made a mistake here, but I'm going to go fix that after I describe something. I think I did make a mistake, but we'll fix it in a second. And I see my mistake. Okay, so I look at this, and hello. Okay, so I can define the control surface like right here if I wanted to, or back a little bit if I wanted to, whatever I wanted to do. What would happen? Okay, what is the pressure at this point? What's the pressure at this point? All of these points, the pressure is 0. If the pressure inside here were greater than that, this is what would happen. So let's assume you had a pipe. You're exiting here. You have a very high pressure at the center. So what does it do actually? It comes out and pushes the particles away from each other, and you have what's commonly called die swell. By the time you get out here, the particles are moving directly to the right. If you go up and down and through this stream, you'll find that pressure is the same. If you go up and down this stream, you'll see the pressure's higher here. That higher pressure turns the fluid away from the center. You don't have die swell here, so therefore the pressure here would be equal to 0, the pressure at the inlet. Let's fix my problem. Oh, I think I did it correct. Okay. I forgot. Okay, so I thought I messed this up, but that is that. 0.05. That's correct. Okay, never mind. It was right. So therefore, what I'm getting at is this. I'll take this. You know what I'm going to do? I'm going to take 2 copies of it. I'm going to take this. I'm going to exchange their locations. And I'm going to put this here. I'm going to do a copy, and then I'm going to do a paste. Oh no, you don't want to do it that way. You want to drop it and then do a paste. And now I'm going to put here, and I'm going to say on the left, what are my forces? You got one force, 0.9, and that's it. Now, it is true it's a surface force, but I'm going to go ahead and draw it as the equivalent force, which I know that's what it's going to be. Do I have any other forces? No. There is a greater pressure down this surface pushing back, like we talked about. But as the particles are turning, and they're all going north or they're all going south, the pressure across these interfaces is 0. Pressure here is 0. Like I said, if the pressure were higher, it would come apart. Pressure were lower, it would draw back. So you would get something called die swell. So that's it. Well, let's look at this. Okay, we've got, so over here, kind of boring, minus 0.9 equals to. All right, you get a flow rate. You get a Q, for example. Q would essentially be this. Okay, so you look at the surface here. You get Vx, V1, let's call it V1x here. You get the velocity here, say call that 2, call this 3. V2, x component, there is no x component here, it's 0. V3, the x component, there is no x component here, it's 0. So all you get is the Vx, or V1, or whatever you want to call it. We'll call this location 1. You get V1 times rho times Q. That's it. Now, if you want, you can say, well, V is equal to Q divided by A. So you could say A1. And he did tell you what the diameter was, 0.01 meters. So essentially, you get this. Q, sorry, I should have put this. This is nothing more than V1. So Q over pi, forgot it already, 0.01 squared over 4. Times, okay, this is water, 1,000, times Q. Now, why do I have a minus here? Why do I have a plus here? I have a plus on this side because I've made a mistake. What mistake did I make? Here's the deal. Here's my control volume, right? My velocity goes in. A normal goes out. This component, therefore, is negative. Therefore, there should be a negative right here. Therefore, I could put this as a negative here, and then I end up with Q is equal to 0.9 times pi times 0.01 squared over the 4 and over the 1,000. And I'm too tired to calculate it. But you can check on that if you wanted to. So I'm going to call it quits now.